One of the more important parts about understanding chemistry gets into understanding something called concentration. Generally speaking, concentration is how we measure the amount of solute per amount of solvent in a solution. So if you look at it here on the right side, you have two diagrams, the concentrated solution on the left and the dilute solution on the right. The one that's concentrated and the dilute solution, they both actually, you can start off by having the same volume, and that's an important baseline to establish. And that way we can evenly compare the two, because that way we can say the concentrated solution has a lot more particles, therefore it's concentrated, and the dilute one has a lot fewer solute particles in that volume of the solution. And that's why we know it's dilute. But again, if you had different volumes, for example, if you had a very, very large volume of this dilute solution, let's say we just multiply that, or open that up, and you have the same concentration. Every so often you have a few of these particles. You could, again, conceivably make that volume so large that the number of particles in the solution is equal to the number of particles in the concentrated solution. Right. But again, the idea here is that we're saying with a baseline of the same volume, we can discuss what concentration is, because it lets us know how many particles of solute are dissolved. How do we concentrate, or how do we calculate these concentrations? One of the most important ones we're going to use is molarity. Molarity is defined as the moles of solute per liter of solution. So a couple things. First of all, we abbreviate, or we start off with the formula having the square brackets, and then inside here you would write whatever substance that your solute is. And that's going to be equal to the moles of solute, which I'll do N, that represents the mole amount, and then solute, I'll write S-O-L-U-T-E, and then per liter of solution, so it's going to be volume of solution, which is often abbreviated S-O-L''N. So that's going to be the concentration of your solution. Specifically, it's the molarity of your solution, and that's calculated by taking the mole amount of your solute divided by the volume of your solution. And so, some of you might be wondering why I'm making so much effort to pay attention to solute versus solutions, because that is, again, different than if you talked about the concentration of your solvent, or alternatively, dividing it by the volume of solvent. This one's specifically saying solute and solution. So be careful as you read through these problems that you identify what your solute and your solutions are. A couple of things about units. This one again, MOL/L. One thing you should know is that the volume that's applied here is per liter. So this V, it's not just generically volume, right? You can't use milliliters. You have to use specifically liters. And then that unit of MOL per liter, that's moles per liter, and that's often abbreviated or often changed to just capital M. Right? Either one of these is perfectly acceptable. You will most frequently see this, and so you'll definitely want to get practice in using that, but definitely know that that represents moles per liter, so they're kind of interchangeable. Finally, how to say this word, or how to pronounce these concentrations. 1.0 capital M, you would just say 1.0 molar solution. 1.0 molar solution. Of course, if you look on the right there, a little chemistry cat joke for you. Enjoy. All right, let's talk about how this works. First of all, with example 1, this is a discussion that involves a 20.5 gram sample of sodium chloride, and it's dissolved in enough water to make 0.750 liters of solution. All right, first of all, solute, solvent. Solute is dissolved into water, so that's going to be sodium chloride, and then the solvent is going to be the water. Now, to be clear about this too, notice how the language did say dissolved in enough water, right? It didn't specify exactly how much water, but the combination of the salt and the water will have that many liters of solution, right? Of the entire solution. Not saying specifically of the solvent. So that's an important distinction. Again, I'm going to reiterate. Number 2, how many moles of solute are dissolved in the solvent? Well, we have a gram amount of solute, which is that 20.5 grams of sodium chloride, and I'm going to convert that into moles, which is something we can do. 58.44 grams of NaCl per 1 mole of NaCl. And that's going to generate 0.351 moles of NaCl. Now, what's the molarity of our solution? And then being sure to use appropriate symbols and units in our work. All right, so what's the molarity of our solution? The molarity, again, of the solution, one of the things it's assuming is that it's the molarity of NaCl, the solute. So in this case, if I start it off, I'm going to have the square brackets, and that's going to be my solute identity, right, whatever it is, NaCl. I'm going to jot that in there in square brackets, and that very distinctly means the mole amount of NaCl, right, divided by the volume of solution. So then I can go and plug some numbers in here, right? That's going to be therefore equal to, let's rewrite that with the actual values in there. That's equal to 0.351 moles that we had from the previous step here. And then divide that by 750 liters of the solution. And do some math, you get 0.468 molar, right? Yes, the units are moles divided by liters, moles per liter, but of course that gets translated into 0.468 molar. So what this is saying that for every 1 liter of solution, you're going to expect 0.468 moles of NaCl is going to be in that sample. And that way we can have a mole amount, right? So if you can imagine all the stoichiometry we've done in the past requires a mole amount. This helps us quantify that without having to actually know an amount. It's a ratio. So for every 1 liter of solution, I know I can get this many moles of sodium chloride. How we accomplished that it was that we were given some amount of sodium chloride per 0.750. So we're basically establishing a baseline of these concentrations, assuming there's always going to be 1 liter of solution. Here's a second example. You're provided 80.0 milliliters of a 0.500 molar HCl solution. Right. So what's our solute? We can go ahead and say that the solute is going to be HCl, right? So when they say 0.500 molar HCl solution, we're just assuming that HCl is that solute, and therefore the solvent is your water. How many moles of solute are in your sample? All right. So remember, the concentration of HCl is given to us as that is going to be the 0.500 molar that was given to us in the problem. But of course, that's also equal to the mole amount of HCl divided by your volume of solution, right? Now, unfortunately, even though we are given a volume of solution, we can't stick 80.0 directly in because that's going to be in milliliters. We have to convert that to liters, so that's going to be 80.0 milliliters. We're going to go through this process and know that's going to be 0.0800 liters of your solution. So let's go and stick the number in here. I'm going to do that, and then we got 0.0800 liters of solution, and then solve for the mole amount of HCl. The mole amount of HCl in a separate step here. Assuming you can rearrange that, no problemo, you're going to get 0.0400 moles of HCl. And then finally, number 3, how many grams of HCl are in the solution? Well, again, we have a mole amount of HCl. We can go ahead and stick that into the setup here. So I'll do that real quick. Boom. And then you have 1.46 grams of HCl. That wasn't that simple. So if you again have 80 milliliters of this solution, there's going to be 1.46 grams of HCl in it. And we know that because if there's 1 liter of HCl, right, the same thing as saying 0.500 molar, that's the same thing as saying 0.500 moles per 1 liter of solution. So using that ratio, I can basically rearrange my math, rearrange to what I need to solve for, and then I can get some other information out of it. Now, example here, for an experiment, you need 0.175 moles of silver nitrate. Your stock room, so the back room here, only has aqueous silver nitrate with a concentration of 0.2500. So what volume in milliliters of the solution do you need for this experiment? All right, so I have this available to me, just a bunch of solution, and the concentration I know is 0.250 molar. I need to get specifically 0.175 moles, right? I need 0.175 particles, effectively, out of that solution. Again, most of it, again, is water, but we need to know that there's some amount of it that's the silver nitrate. How do we set this up? Well, again, silver nitrate, first of all, is AgCl. The concentration of AgCl is equal to 0.250 molar, as given to me in the problem. I need to obtain 0.175 moles, so if I set this up, right, I need to get 0.175 moles of AgCl, but I don't know how much volume of my solution I'll need to obtain, so that within it, it's going to contain 0.175 moles. All right, do a little rearranging here. So my volume of solution is equal to 700 or 0.700 liters. Right, doing a little fast math there. And of course, since the problem is asking for the volume in milliliters, you're going to have to take that 0.700 liters, convert it into milliliters for every 1 liter. It's 1,000 milliliters, and you end up getting 700 milliliters. All right. So let's see how we can change concentrations. All right, so we have a generic solution. It's going to be a 0.100 molar solution of glucose, and it's hanging out at room temperature. So what's going to happen to the concentration if you do a bunch of these things, these 6 things to it? So again, if you can imagine, right, I have myself a container of glucose and these little particles that are floating around. They're arranged, or there's enough so that it has 0.100 molar. So effectively, what am I going to do, or what can I do to the concentration if I apply these different changes? So 1, more water is added to your solution, right? So just plain water. If I add more water, right, but I don't add any more of the glucose that might be dissolved in there, that means my concentration experiences a decrease, right? Because I have the same number of particles of glucose, but a larger volume of solution. It's going to decrease my concentration. The beaker's left out for a week, right? Well, as you can imagine, if you leave out a watery substance for a week, a lot of the water itself can vaporize, but it leaves behind glucose. Glucose is not just going to magically start to evaporate. And so we decrease the volume, but then we also have the same number of particles. So that's going to increase, right? And by the way, in case you're wondering, right, remember, I'm going to do this, the mole amount divided by volume. So if I decrease the volume, right, by leaving it out for a week, I'm going to leave my solution, that means my mole amount stays the same. So if the denominator goes down, the overall value should increase. The solution is cooled down by 10 degrees Celsius, cooling it down some. Now this one can be a little tricky, but cooling it down really shouldn't change a whole lot. Your initial, honestly, your main response here can really be no change, right? If you change it, you're not really changing the amount of volume. But if you decrease the temperature a little bit, you can make the argument that sure, you change the volume of it by some, but it's so negligible that really it's practically no change. So I'm going to say for this one, no change. Quarter of the solution is removed and placed into another beaker. All right, so I take out a quarter of the solution. So let's go ahead and kind of chunk this bad boy out. That's about a quarter of it, right? Well, again, the actual ratio of particles to volume is still more or less the same. So at the end of the day, this one's going to be no change. 20 milliliters of oil is added to your solution. Right. Well, what do we know about oil? When oil is nonpolar, the solution is made of very polar water. Those two substances will not combine or mix in any way. And so effectively what you have is just a layer of oil resting on top of the layer of solution. So what happens to the concentration of glucose in your solution? Nothing. So this would be no change. Finally, 20 milliliters of another glucose solution with equal concentration is added. Right, so my ratio of moles to volume is still 0.100. I combine it with the original concentration of 0.100. Well, again, the ratio of moles to volume remains the same, so that's going to be no change. Right. You may have added more volume, but remember that volume is not just water. It's water and the dissolved glucose within it. Let's talk about dilutions. Dilutions is where you can lower the concentration of a solution by adding a solvent. So a couple terms. Stock solution is your original solution. That's the most concentrated, untouched solution. Diluted solution, as you can imagine, is a solution that has lower concentration than the stock solution. So you've basically watered it down. You've diluted it down. If a solution is diluted, which are the following changes? Concentration, amount of solute, amount of solvent. So again, if we talk about diluting something, we're adding just plain old water. We're not adding any additional solute. So my concentration is going to go down. What about my amount of solute? My amount of solute actually stays the same. There's no change there because the amount of solute isn't increasing or decreasing, but it is being dissolved in greater volumes of your water. And the amount of solvent, therefore, that is going to go up. So overall, let's go ahead and apply that concept of how this works. So remember that this dilution calculation, or this is going to be helpful in terms of calculating with dilutions. So the important thing is that the quantity of solute remains unchanged in a dilution. So remember that we just talked about that, right? The number of particles that are dissolved are not going to change just because you add extra solvent, right? The number of particles are still there. It's just that now it's watered down some. So the mole amount of your solute before your dilution is equal to the mole amount of your solute after your dilution. Right? Generically speaking, remember that when you have this formula, so kind of applying this, right, the concentration of something, whatever it is equal to the mole divided by the volume of your solution. Right? Therefore, if I rearrange it, can't you also then get N, your mole amount of solid, is equal to your concentration times the volume, right? So if you just rearrange this to solve for moles of solid, don't you get this, right? So basically moving this up here, cross multiplying that. So this is basically how this works. For any dilutions that happen, the following formulas can be applied. So you have a square bracket S times Vs, right? Because what's that equal to? That equals to the mole amount. Okay, and that's right here, the mole amount. So the brackets, right, that's represent the concentration times the volume, that's equal to a mole amount. And that's going to have the S abbreviation, or S sort of subscript there, that's representing stock. And then over here you have D and D, which again are the same concentration, or you have some value of concentration and volume. Well, what do you know about D and D here? That's going to be your diluted, right? It's going to be diluted solution quantity. So the concentration of your diluted solution times the volume of your diluted solution, that's also going to equal to a mole amount, right? And well, that's going to be the mole amount of the solute that you calculated here. So the mole amount of solute is still the same between these two. It's just that the concentration and the volumes that are applied are going to be a little bit different. Alternatively, you can just use square bracket 1 times V1 is equal to square bracket 2 times V2, where the 1 and 2 just means solution 1, solution 2, condition 1, condition 2. You get the idea. Ultimately, remember, the key to this formula is knowing that the mole amount of your solute before and after dilution remains the same. Right, that's kind of the key point there. Let's put this in action. A 0.250 liter sample of 0.0500 molar Na2 solution, Na2SO4 solution, is diluted by adding enough water to make 0.650 liters of solution. What's the molarity of that diluted solution? All right. So what do we know? We do have a stock solution here, so I'm just going to abbreviate that S. That's my volume, volume S. And I have a concentration here of this substance. That's my stock solution again. And we know that because that solution was then diluted. So we know these are going to be your stock values. We're going to add enough water to make this volume of solution. So we know that this is your diluted volume. And then what's the molarity of my diluted solution? So here we go. We know that my concentration of my stock solution times the volume of my stock solution is equal to the concentration of my diluted solution times the volume of my diluted solution. Again, we know this is valid because the result of these numbers gives you the same mole amount. Right? We have not changed the amount of particles that are dissolved, just the volume that they're dissolved in. So we plug in the numbers that we know. We have 0.0500 molar of my stock times the 0.250 liters. That's equal to whatever this value is, that diluted stock solution. And then we have the volume of my solution, which is now diluted solution, which is 0.650 liters. And real quick, I should have done this earlier, so I apologize for the late correction. These actually should have the identity in here, right? So we jot these in, Na2SO4, Na2SO4. And so I write those in there because I know this is the concentration that we're being used, or that's focused on. And then we solve for that last bit. So that, again, doing what you got to do, Na2SO4, sodium sulfate. My diluted concentration is going to equal to 0.0192 molar. That's all you have to do. So by diluting it, right, by adding a bunch more volume apparently, or adding a lot more water to it, I increase the volume of my concentration, or the volume of my solution, but I end up lowering my concentration, right, from 0.050 now to 0.0192. One last thought here, remember that you do have to make units work out consistently, so when you solve for this, your concentration should of course be in molar, but also make sure you're aware that, the volume here, liters here, but if you started with milliliters and put them in on both sides, those units will cancel out, so you don't have to convert them between liters and milliliters, as long as both sides have the same consistent unit of volume. Alright, that'll do it.